Bismillahirrahmanirrahim. Assalamu alaikum dear students. This is our next problem. Problem having been chosen from the book Quantum Physics by Stephen Gasiorowicz. As usual, we first come to its statement, okay? Radiation of wavelength lambda equal to 290 nanometer, nano standing for 10 to power minus 9. Lambda equal to 290 nanometer falls on a metal surface for which the work function is W equal to 4.05 electron volt. What potential is needed to stop the most energetic photoelectrons? Dear students, we have dealt with a similar problem having been chosen from the book Concepts of Quantum Concepts and Applications in Quantum Mechanics by Nordine Zetley. Okay, to some extent that problem is being repeated with different values under different circumstances. Okay, before starting its problem, before starting its solution in a formal manner, we are going to introduce a few snapshots which will serve as a foundation regarding the easier understanding of the solution. Okay, so from this is a table of physical constants. This table has been taken into consideration several times in our previous problems, previous videos. We may pick any physical constant which may need in our solution. In this solution, particularly this value, that is Hc equal to 1240 electron volt into nanometer or million electron volt into femtometer, this will be used. Okay, while dear students, this is actually Planck's constant h multiplied by speed of light c. Value of speed of light is separately given at first serial. Okay, c equal to 2.998 into 10 raised to the power 8 meter per second. Moreover, value of Planck's constant h is also given as 6.626 into 10 raised to the power minus 34 joule second, which is alternatively equal to 4.136 into 10 raised to the power minus 15 electron volt into second. Okay, separately these two values have been given, and combinedly their product is also given in this table of physical constants. Okay, so it is a matter of discretion whether we take separate values or combined values. Next snapshot is about photoelectric effect. This philosophy will be applied in this problem. Okay, photoelectric effect. Okay, EV naught is equal to HF minus phi. Phi is work function. Okay, where EV naught is the maximum kinetic energy of photoelectron, in which E is the magnitude of electron charge and V naught is the stopping potential. H is energy. HF is the energy of absorbed photon, in which H is Planck's constant and F is light frequency. Phi is work function. Okay, now we are going to say something about work function more. Okay, work function, a quantity that determines the extent to which thermionic or photoelectric emission will occur according to the Richardson equation or Einstein's photoelectric equation. Okay, it is sometimes expressed as a potential difference symbol, psi or phi, in between psi or phi. Okay, in volts, and sometimes as the energy required to remove an electron, symbol W, in electron volts or joules. The former has been called the work function potential and the later the work function energy. Okay, work function potential and work function energy. Now, dear students, next snapshot, a table of Greek alphabet has been shown. Actually, the purpose of this table will be to ensure whether we are pronouncing this symbol correctly or not. Okay, so we try to find out whether this symbol occurs in this table or not. So dear students, I think exactly this symbol perhaps does not appear in this table. However, this symbol is very closely related to these two symbols phi and psi. Okay, phi is this and psi is this. Okay, so we can also treat it as a phi or psi. Anyhow, mm, it is not our basic requirement that what this symbol is called. Okay, this symbol, that is this symbol is almost phi or psi. So we have tried to know the name of this symbol. Now next, now we are going to start our problem in a formal manner. Okay, we know that H nu, this is also a Greek alphabet nu. This is given in that table. Let us go back. Nu or nu, here. V type, nu. Yes, this nu, new. Capital N is its uppercase, and this V like italic, this V. Okay, this nu, new, capital N, this V like symbol. Okay, this is new. So dear students, H nu is equal to Hc over lambda. This alternatively becomes equal to work function W plus kinetic energy K. From this expression we reshape this equation as K. This implies that kinetic energy K is equal to Hc over lambda minus W. This is equation number 1. Okay, where H nu is photon energy, in which H is Planck's constant and nu is equal to C over lambda is the frequency of photon. Okay, W is the work function of the metal and K is the kinetic energy of the electron leaving the metal. Okay, using Hc equal to 1240 electron volt into nanometer. Okay, dear students, this value is that which is given in the table number 1, table which has been shown as a first snapshot in this video, and I had told that value of H separately is also given and value of C separately is also given, and combined value of Hc is also given. So we are utilizing combined value. Then wavelength lambda is equal to 290 nanometer, nano standing for 10 to power minus 9. This value is provided in this statement. Moreover, work function W is equal to 4.05 electron volt. This value has also been provided in the statement. Okay, so two values have been provided in the statement, while third value has been taken from a table of physical constants. Okay, so using all these values in equation number 1, we get kinetic energy K equal to this over this minus this. Okay, this. Okay, so after simplification, our kinetic energy becomes equal to 0.22586 electron volt. This is kinetic energy electron volt, but we are required to find just the value of V, potential difference. So this implies that potential difference is 0.22586 volt. Okay, what we have done, we have just simply ignored electron volt. From electron volt we have ignored electron, and then simply V is the potential difference. So okay, I think matter is solved. This is the end of our problem. This is the end of our video. Till next video, Allah Hafiz.